Welcome to Convergent Dialogues. This is Xavier Bonilla. On this episode, I'm very excited to be talking with Riley Black. Riley is a vertebrate paleontologist and science writer. She has written for numerous outlets such as Scientific American, Smithsonian Magazine, National Geographic, and many others. She's also written many books on dinosaurs. And her latest book is called The Last Days of the Dinosaurs, an Asteroid, Extinction, and the Beginning of Our World. And that is the book that we discuss in the conversation. We start by talking about her background and some of her reasons for writing this recent book. We talk about what life on Earth was like with dinosaurs being very prominent and leading all the way up to the asteroid event. We talk about why dinosaurs were so successful in diversifying. We talk about the importance of fossils to tell the story of dinosaurs. We spend a good amount of time talking about the asteroid hitting the Earth and many of the ripple effects and impact that had on the Earth for many years. We talk about the animals that did survive after the asteroid and how Earth survived years following the impact. We talk also about a little bit of how plants were able to continue in the post-impact Earth and how this was important for life to happen again. And we also talk about how the period where dinosaurs were prominent compares to how mammals and to a larger extent humans are prominent now. I have to say, anytime I'm going to get somebody on the podcast that is talking about dinosaurs, the kid in me comes out again, as I think it will for many listeners too. Riley is fantastic. She has a big passion for this topic. She's devoted, her entire life for this. She's absolutely wonderful. I was really honored and fortunate to talk with her about, her work and her writing and her fantastic book, which is really great. We talk about it in the conversation, the way in which she writes the book, and really talking about an event that is almost kind of just glossed over, and really just focusing on what the asteroid did to the Earth and what it did to dinosaurs. And so now I bring you Riley Black. I'm here with Riley Black. Riley, thank you so much for coming on the podcast. I'm very excited to talk with you about your wonderful book. So big thanks to you.
Oh, it's a pleasure. Thank you for having me on.
Yeah. So tell listeners who you are, what you do, and what you're currently researching, and all the wonderful particulars.
Oh, sure. Well, I'm a freelancer by trade. So like when I talk about what I'm doing, it's kind of all over the map. So my name is Riley Black. My pronouns are she, her. I'm a science writer and author. So I've written, it'll be 10 books as of the end of this month, hoping to get started number 11.
Wow.
And The Last Days of the Dinosaurs is the newest one.
Wow.
But I also freelance for a lot of different publications like National Geographic and Smithsonian, Scientific American, Slate. Really, if somebody needs commentary about a fossil or reporting about a fossil, I'm often the person who's doing it. But I also go out in the field every summer, usually between about this time of year, about mid-March through through around September. I usually go with different field crews from different museums and different universities and go look for new fossils. And it really helps feed my writing and like what I know and I understand, because what you get from a technical paper versus a press release versus the actual experience are all different things. So that's kind of what I do. It's like my career is as a science writer and science journalist, but that really helps feed this just like passion for fossils and prehistoric life that I get out there every chance I can get.
Yeah, that's such a cool gig to just spend, I guess, what is that, 4 or 5 months, or I guess longer, I guess about half a year, just digging around for fossils. That's so cool. And then you get to write about it. That's like such a cool job. Your background is in paleontology, or what's the background? And I forget.
Yeah, so I'm actually a failed university student. So I went to Rutgers University in New Jersey for marine science, and then realized I'd mostly be studying like ocean chemistry, and I wanted to study sharks and stuff. So that didn't necessarily work. So I switched over to ecology and evolution there. Nice. And again, it was one of those things where like nobody ever tells you when you're going to college that you're going to be studying kind of the sub-discipline or interest that your professors are specialists in. It's just kind of like, oh, they have an ecology program. That sounds good. I wanted to say like the ecology of like carnivores and herbivores and things like that. It's like we study wetland ecology. I'm like, okay, well, that doesn't really work either. So while I was there, I used that great university library access to get access to journal papers and to books, and I started blogging as a result of that. So that was really my training. Like I knew enough through my coursework to understand like how to do research and how to think scientifically, and I've loved science ever since I was a kid. But this was really like self-driven work, and I wrote about it to help myself remember it, because that's the idea of like, if somebody tells you something, you may or may not remember it. But if somebody tells you something, you learn something and you process it and you explain it to somebody else and you kind of write it out, you're more likely to remember it. So that was my logic at the time. And it kind of started this writing career that I've been in for professionally over a decade now, probably a little bit longer than that if you take it back to college. But yeah, that's how I got my training. It was sort of this cornucopia of different biological sciences, and I applied that to actually learning more about the animals that I wanted to know about, because I was tired of reading news reports or watching the documentaries. I was like, okay, what are they actually saying in these papers, and like how much do we know? Like when you learn about a particular dinosaur, like that's really cool, that's so neat, and then you go look at the paper, it's like we have 3 bones, and most of what we think is based upon something else. It's like that's the stuff that I wanted to know, and like why do we do this?
That's funny. Yeah. That's super cool. That's a really cool, like I say it a lot with many writers and guests that I have on, is people take different ways up the mountain to get there, right? Some it's rarely the direct path. It certainly wasn't for me either. It was the long way around, and so that's super cool. I mean, my goodness, you have 10 books published already, right? I mean, that's quite an accomplishment. The most recent one, which we're going to talk about, is The Last Days of the Dinosaurs, an Asteroid, Extinction, and the Beginning of Our World. Also a cool subtitle. I guess just before we get into the details of it, what inspired you to write this book? And the way in which you wrote it. I know you talk about that in the appendix, but there's a certain way in which you write the book, almost like a narrative account of sorts, which is super cool, it makes it for a really good reading. So yeah, why this book, and why did you decide to write it that way?
Right. So I was thinking about what book I wanted to do next. So I just published Skeleton Keys, which was my last book about the human skeleton, sort of its origins, its natural history, its unnatural history. And I kind of want to get back to paleontology again. And I'd actually been given, not an offer, but there was some interest in having me ghostwrite a book for another paleontologist who specialized on the extinction that ended the Cretaceous, that famous, extinction that decimated the dinosaurs. And I thought, like, I don't think I want to write for somebody else. I think I want to tell the story the way that I want to tell it. And a lot of what drew me to it was very personal, in that at the time I was just starting to go through a divorce. I had just come out as transgender and started my transition. So I felt like in my life, it was like this extinction event, or like one day everything is just kind of, the way that it's been for millions of years, relatively speaking. And then the next day it's entirely different and you don't know what's going on. And I really attached to this idea of the world basically ending in a very short amount of time, like a 24-hour period, more or less. But then there's this great story of recovery, and everything comes back and it's different, but it's just as vibrant, it's just as interesting. So I took that as a kind of personal metaphor, but I realized that no one really told that story before. We kind of yada the extinction of the non-avian dinosaurs and all those other critters, where it's like we take it as obvious that a big chunk of rock hits the planet, there's going to be a mass extinction. It's like, well, that's not necessarily true. And the way that this played out really was the worst case scenario at the end of the Cretaceous period. So I really wanted to go through that and talk about, well, what happened and what order, and does that explain something about the world that we're in now? Because even though 66 million years is a very, very, very long time, it's actually relatively short compared to like how long the non-avian dinosaurs were around. So it was one of these things where we can still see echoes of it around us. So between that personal aspect and just looking to the story that like no one had really gone into in detail, there are plenty of books about sort of the scientific controversies and all that sort of stuff, but like what actually happened to the best of our knowledge, it really just kept drawing me in. And I wanted to tell that story sort of on the ground rather than going and talking to this or that expert and doing the very standard pop science thing. I wanted to try something new, something different, something that I hadn't done before. I really like scientifically informed narrative. So like you mentioned, I split the book basically into two halves. There's the main body of the text, which is like, if you were there, what would you be seeing? What's going on? Kind of trying to direct sort of the reader's gaze here and there. So okay, this is kind of what's going on, and these are the consequences. And then stepping back in the appendix and saying, okay, this is why I'm telling the story this way. And like, we know this for a fact. This thing we don't know for a fact. This thing is speculation. This thing we can go look at the evidence for, and really spell that out, because there are certain things that I say in the book that I might be wrong about. And that's the fun part of science is, you have to show your work. So that's what really drove me and attracted me to that story. It seemed to be this big gap in the discussion about, what happened for something that like we all think we know something about, right? You learn that as a kid. The dinosaurs were around, asteroid struck, and then it was over. It was like, well, it's not quite that simple. And when you look into it, it's like, oh my gosh, this really was pretty much like the worst 24 hours. We can span that out into 3 years, but like the worst day the Earth has ever had. And I just found that super compelling.
Yeah, no, it's really nice the way you put it. I guess I just kind of on the personal side of things. Now that the book's written and you've completed it, and it's soon to be out and everything, what is you talked about how there was kind of your own personal experience of this kind of ending and rebirth or restarting of this kind of thing, this kind of comparison you're making. And so, I mean, now that it's written and when you're done with it and all this stuff, like, how does it feel kind of looking back on, like, here's the story of the asteroid and then the dinosaurs not being here, or non-avian dinosaurs, and then just kind of knowing how much it was for you personally, just kind of when you take the step back and look at it from 30,000 foot view, what is it all like? Where does it all kind of land for you? How does it all kind of feel, I guess?
Yeah, I feel hopeful about it, for lack of a better term. It's hard to encapsulate all my feelings about it, because I started working on this around the time that I was just starting to get on hormones, that I was just starting to change. So in a way, like, as I was writing this book, it was being written during a time that I was very much going through my own personal changes. So like, it's not in a direct way, it's not a memoir, but right. I can look at it and say, okay, like, I was interested in this aspect or this story because of something that I was feeling or experiencing or worried about or hopeful about. So seeing it now is kind of like a time capsule almost for myself of those 2 years that I was working on that project. Because like, I don't know how familiar you are with like sort of the process of what these transitions entail, but like for me, I was, assigned male at birth. I went under feminizing hormones. You are so tired for that first year, like as your body adjusts to the new hormone levels and your testosterone drops and your estrogen goes up and all that stuff, that there was definitely this sense of, I related a lot to those, earliest days of the Paleocene, that time period after the Cretaceous, where it's like life hadn't started to come back yet. There was the sort of remnants of what was once there, and change was starting to occur, but it's over this broad time scale, and you're just kind of like almost anxious to see what's going to happen next. Like, what is this going to thrive into? And I very much felt that. So looking back, I can still very much relate to that time period in my own life, and to see it done. I mean, I'm honestly just happy to see my real name on this book. This is not the first book overall. I have a children's book and a coffee table book that have my real name on it, but this is the first book that I feel is like entirely mine, that I came up with the idea and did the research and told the narrative, all that stuff, that has my real name on it. And that, to me, it's a big deal. It's great to see this kind of debut after a decade of writing to sort of come back at it again, as I always should have been.
Yeah, no, it's really nice. I mean, I can kind of hear in your voice, and I can see like just how much it means to you, and that's special. That's special. Kind of, you're saying, to have a time capsule of, still doing something that you love and you've been doing for a good part of your life, and then, like you're saying, doing it in a way that feels like with your name on it, like your real name on it, like this. There's a kind of like, almost, I can imagine some type of hope, or kind of like comfort. Yes, like this feels right. This is how it should be, and I can just see how much that means. So it's great. I can't help but wonder if kind of some of the kind of whole process, and then kind of your kind of positive outlook on it now. I don't know if it just came through in the writing, but it was just really good. It was just really, really good. The writing's good, and how it comes out, and telling a story that, you're right, it's not like you just, wrote another dinosaur book. Like, it's something that, doesn't get talked about a lot. It's like, yep, it happened. Okay. And then what happened before, what happened after, but not many people center around the event of the asteroid. So it's really cool. I think it's really, really cool how it all ties in.
Oh, thank you. And that's something that I want to do. Like I wanted something that was a little bit different from what I've done in the past and what else has been out there. I feel like a lot of paleontology books, even some of the books that I've written, have been very much in a standard mode, whether it's either very historical, very autobiographical, or kind of like an info dump. Mm-hmm. But in thinking about how I wanted to approach this, thinking people often respond to narrative more than they do just like, here's a list of facts. Like, it's awesome to have an encyclopedia and be able to look something up, and you take that snippet and you put it into something else. Right. But I was thinking about books like Raptor Red, which Bob Bacher wrote a number of years ago. Mm-hmm. And that was a book that I think mine is a little bit more scientifically grounded. His was a little bit more overall just kind of like an adventure, almost like fantasy kind of book. But I liked that approach of like, okay, I can tell these stories about coevolution, about the consequences of this impact and what happened, by putting us there and kind of directing the reader's gaze to one point or another. So it's not just, I tried very hard to avoid anthropomorphizing many of these animals. I mean, to some degree, you're giving them personalities and sort of motivations and things like that. But I figured by kind of picking some of these vignettes, like by talking about like, well, what are the ferns doing? What are the birds doing? What are the lizards doing? What are the, microorganisms that live upon or once lived upon the non-avian dinosaurs doing after this, and kind of zooming in a little bit and talking about their biology and what their history is. There's kind of like writing a bunch of biographies for organisms I'll never get to meet in life, but using the best information that we can. And it was just fun to do. I felt I was having a little bit of trepidation at the beginning. One of those, like, can I really like pull this off? This isn't going to be too cheesy, is it? But like, as I got into it more, it started to really unfold and all these questions started to appear. For example, like, we don't have a lot of great fossils from what we call the boundary layer, basically the layer that documents the very end of the Cretaceous and the beginning of the Paleocene, where we find that iridium spike that tells us an asteroid hit. There's one site in the Dakotas that's probably from about that time that might be really good. But in general, there's like this basically 6 feet or more where you don't find a whole lot of fossils leading up to that boundary. So I kept wondering, why is that? Like, we know the animals were there. They didn't just like disappear, weeks or months ahead of impact. And I was thinking about how I want to do this, and I was reading up on fossil lakes at the time. And I came across this paper about these little things called ostracods, these little invertebrates that have shells that are actually really great for learning about paleo environments. They're not the sexiest of animals, but they're really useful. And you see their fossil record kind of fizzle out around the boundary when it shouldn't. And it's probably because of acidification, of acid rain, of this influx of acids into the environments that also would have affected things like bones. So we would have had a very different fossil record without some of these consequences. And I just loved learning things about that. Like, every time I learned something like that, I felt like it opened another avenue to talk about these things.
Yeah, no, I think I could definitely see some of the risk in telling the story that way, but I'm glad you took it, because it really it was definitely different in a good way. And yeah, I think writing about like the asteroid hitting and what it did in a kind of like, very pop sciencey information way would have maybe been a little bit dry. And so I think the way that you tell the story is great. So let's, I guess, just kind of start before we get into it, kind of the overview of kind of the history of dinosaurs. So just kind of give us many people will know, kind of loosely about the dinosaurs, or maybe people just watch Jurassic Park and that's all they know, but whatever. But, just kind of tell us about, history of dinosaurs, how they arose, they grew in size, they dominated the earth, they were the bosses of the planet, and then just kind of lead us right up to in the Jurassic, from going from the Triassic to the Jurassic period, right before the asteroid hit. So just kind of give us the sort of kind of origins, how they got to dominance, and then right before the event.
Right. So when we're talking about, dinosaurs, and they're still with us, I mean, birds are dinosaurs. So that's why I kept saying non-avian dinosaurs. So there's not a great non-technical term
Right.
for it, unfortunately. And this is part of the history of science, is that it took us that long to realize that birds are dinosaurs. So now we're kind of going backwards and saying, like, okay, well, we'll make this split, and there's not a great way to otherwise work it out. So it really starts about 252 million years ago with the worst mass extinction that the world has ever seen. And this is what really gets me about the history of dinosaurs, right? Is that we're often focused on like why our favorites like T-Rex and Triceratops disappeared, when dinosaurs were the recipients of sort of good fortune from previous mass extinctions. So 252 million years ago. That's the end of the Permian period.
So this is the Great Dying, right? Into the Cambrian explosion? Right, yeah.
The Cambrian explosion is way earlier, but this is the This is the Great Dying. This is basically, you have a whole bunch of volcanic activity that spews just like tons and tons and tons and tons of greenhouse gases into the atmosphere. It lowers oxygen content. It raises the acidity in the oceans. Like 75% of species that we know about, and it's even higher in the oceans, I think, if we just look at the seas, go extinct within this time frame. And just life on Earth is just devastated. But in the wake of that, you have the surviving species. So previous to the extinction, the most numerous and diverse vertebrates on land were our relatives and ancestors, the proto-mammals, things that we call synapsids. So if you've ever seen Dimetrodon, which lived a bit earlier than that, but it's those kinds of animals. They kind of have some traits that are kind of reptilian, but they're more closely related to us, and they're starting to get these mammal-like traits. They were the most numerous and definitely like the most ecologically significant on land, but they're almost entirely taken out. They're just like two groups that make it through. And it's really reptiles at the beginning of the next period called the Triassic. So that kicks off 252 million years ago to about 201 million years ago that really proliferate. And the first ones out of the gate are all these croc relatives, all these weird things that go into the seas. And amongst them, these little fuzzy little creatures that are kind of hopping through the undergrowth, like going after beetles and things. And those are the ancestors of things like dinosaurs and pterosaurs. So those flying reptiles that you see through a lot of the Age of Reptiles stuff. So by about 243 million years ago, so obviously millions of years are a long time, but relatively speaking, soon after that mass extinction, you have the very first dinosaurs start to appear, the first things that we can recognize and say, okay, this has some of the critical traits that are related to all these other ones. But dinosaurs are they're not the stars during the Triassic. They start to diversify and split into their major families. You have some big herbivores by the end of the Triassic, these big sort of predecessors of things like Apatosaurus. So these dinosaurs that are really weird. They've got small heads and long necks and big bodies, but they're still walking on two legs. And that's about as big and as prominent as they got in these little carnivores, but it's mostly other sorts of reptiles, croc relatives, that are kind of running the show. And then they run to another mass extinction about 201 million years ago. Again, it's volcanic activity this time, like in the ancient Atlantic, has very similar effects. The dinosaurs are relatively unscathed, but the croc relatives are almost entirely taken out. And that's what begins sort of the true age of dinosaurs. So dinosaurs show up after this terrible mass extinction. They're kind of on the sidelines. Then another mass extinction kind of hands them this good fortune. And then their evolution just explodes. You start to get the earliest armored dinosaurs, the first predatory dinosaurs like crests, things like Dilophosaurus, if you've seen Jurassic Park, is from the earliest part of the Jurassic. And that sort of continues over the next tens of millions of years. So all the way through the Jurassic and all the way through the Cretaceous, you have all these different lineages of dinosaurs proliferating from small size to large size. It's something I try and avoid saying that they dominated the planet. There's a great book called Full House by one of my inspirations named Stephen Jay Gould, where he says, if we think about sort of the most numerous, the most influential, we've been in the age of bacteria for about 3.5 billion years, and we still kind of are. But yeah, it's something that I think is very human to say dinosaurs are dominating the planet because we want to relate to it. And I know I've said it in some of my books, since one of those things I've recently started to question, is there a better way I could talk about this? But in any case, they were the most sort of significant vertebrates on the planet. They're basically the equivalent of mammals and birds and critters like that today. So that leads us up, through the end of the Cretaceous through a time where they're still diversifying, that they still exist over the entire planet. So if we were to go to like the day before the asteroid strike, like there wouldn't be any sign that they're basically impending doom. Like you wouldn't be able to tell that something bad was about to happen. Dinosaurs weren't on the decline. They weren't starting to falter. It's just they were continuing on as they always had. It's just a huge span of time. Even just from that perspective, there's 66 million years between us and the last T-Rex, but there's over 80 million years between T-Rex and dinosaurs like Apatosaurus and Stegosaurus. And that's not even getting to the beginning. So you could fit the entire like post T-Rex history of the world between those two famous dinosaurs and still have like over 10 million years to spare. And like that's how long they were influential on this planet. So like even though it's been quite a while since they've been extinct, like they had this huge influence on so much of what we still see around us. And that's really like the importance of the age of reptiles. It wasn't even so much that dinosaurs kind of came to prominence and just held on. A lot of things that are important to us now, like flowers and like pollinators and things, all evolved in this context of a world where dinosaurs were common.
What is it? I mean, maybe it's hard to know, but what is it that was so, obviously there's other animals as well, but what was it about dinosaurs that they were just able to diversify so much? Again, it's millions of years, but and there's so many different, obviously types, and they were huge. I mean, not maybe the biggest on the planet ever. I think the blue whale takes that title, but they were massive, and different types were massive. I mean, what was it? I mean, what can we say confidently, or is it maybe speculative as to why they diversified so much?
Yeah, we're still working that out. Like, why were dinosaurs so basically successful, for lack of a better term? Like, why were they so diverse and held on for so long? It's really kind of strange in a sense that we didn't have another mass extinction between the Triassic and the Cretaceous. It's still a huge chunk of time where if you look at the previous mass extinctions, they happened at not a greater frequency as in like, every million years or so, but they were closer in time to each other, and dinosaurs did really well for a really spectacular amount of time. So in terms of, if we go back to like in the wake of the Great Dying, in the wake of the Permian mass extinction, that reptiles were able to reproduce much faster than a lot of the surviving proto-mammals were. So there's a hypothesis, and there's been some data-driven research on this based upon like body size and where you find fossils and sort of looking at the pattern over time that suggests that archosaurs, which is the group that dinosaurs belong to, as well as birds, as well as crocodiles, basically all this great family of reptiles, they reach sexual maturity earlier in life. And since they laid eggs, they were able to basically have more offspring. And because they were outsourcing their reproduction, they weren't keeping those eggs inside as mammals would eventually do. They were able to grow to larger sizes, because that's a problem that we see amongst large animals today, like elephants and giraffes and things. They typically have a small number of offspring that they have to gestate for a very long amount of time, like almost 2 years in some cases. A lot can go wrong. So it's like the slower reproductive route if you're going to gestate internally versus you lay an egg and the constraints are kind of come off for that. And that's what allowed them to get from small size to absolutely gigantic sizes. Like even though the blue whale is technically the biggest, there's never been anything bigger on land, than some dinosaurs. And it wasn't even just once, it was multiple times over tens of millions of years. You're getting animals that are longer than 100 feet long and weighing up to 70 tons or so. I mean, that's really super impressive. So it seems like they were just able to reproduce at such a rate that they were very evolutionarily responsive, that they could adapt to a lot of the climate changes in vegetation, coevolution, all these sorts of things, that like they were given a little bit of an evolutionary edge just by chance. And then when a mass extinction kind of handed them this good fortune, that they kind of inherited this planet that's free of their competitors, their evolution just took off and they filled it up before any other creatures could do so. That's one of the reasons why mammals were probably relatively small during the Jurassic and the Cretaceous. It's not that they weren't diverse. We're actually learning that mammals were incredibly diverse and different during the age of dinosaurs, but they couldn't get very big without being picked off, because dinosaurs had already filled up so many of those niches. And it wasn't until after they disappeared that we get the mammals that we're familiar with now. So really a large part of dinosaurian success was they picked up these really basic biological traits. And when, good fortune basically smiled on them, they were just able to run with it in a way that other organisms just is pretty much unprecedented in the history of life on Earth so far.
Yeah, I think it's interesting that, again, your answer is a really good one. I hadn't heard that before. It makes sense, I guess, intuitively about the whole, like, if you're having eggs, well, that's a lot different than if you're, having to gestate and, you can't, produce as many. And then about the mammals thing, I think that's also true. I think, right, that's what you were saying, that many folks have been sort of realizing that now. It's like, oh, like mammals weren't entirely after the dinosaurs. They actually were right along with dinosaurs, but were really small, or precursors to mammals, or kind of in that early stage. I'm forgetting the name. Steve, what am I forgetting? He wrote The Rise and Fall of Dinosaurs.
Bruzzati. Yes.
Bruzzati, yeah. He talks about this, and I think his new book kind of talks about that as well, and about mammals. And so it's interesting to see people discuss about because right, like that's the whole thing is, could people saying, could humans and dinosaurs live together? That's always like a interesting thought experiment. But what about mammals, right? And so we're seeing that maybe mammals and dinosaurs, very small mammals, but were maybe living for a time together. So it's a very interesting thing.
Yeah, the earliest mammals that we know of, there's some controversy about what constitutes a true mammal in an evolutionary sense versus their ancestral group. So a lot of these things are nested in what we call clades, which is basically a family group of whatever rank. So mammals belong to a group called mammaliaforms. And the difference between a mammaliaform and a true mammal is very much debated still.
Right.
But if you want to talk about something that more or less looks like, if you look at it, you'd say that's a mammal. It's fuzzy. It's got multiple different kinds of differentiated teeth. It has the sort of mammalian ears and all the stuff that we would recognize. Those show up about the same time as the earliest dinosaurs do. And I really love a lot of the recent research that's been coming out saying, like, we used to have this idea that, and I think it's more of a trope, really, that mammals in the age of dinosaurs, they lived under the feet of dinosaurs or in the shadow of the dinosaurs, and they're all insectivores and they all came out at night. Well, especially in the last 20 to 30 years, there are mammals that lived amongst the dinosaurs that were the equivalents of beavers and otters and raccoons and aardvarks and flying squirrels, and had all these really fantastic adaptations. They didn't get very big, but they were definitely lived in all these disparate sorts of ways that have modern equivalents. So they kind of had this little explosion at small size, that allowed them to hang on and proliferate. And they kind of played the same trick that the dinosaurs did. A mass extinction handed them good luck, and they really took off. It didn't have to be that way. We could have wound up with a second age of reptiles based upon crocs and birds and things. But even with birds, I feel like, and you hit on this, that there's a idea or a belief that you have this world that's full of all these gnarly reptile kind of things, and then that ends, and that's when you get mammals and birds and stuff, when really it's no, those were there all along. They're actually interacting. They have relationships with each other and influenced each other's evolution. The earliest birds that we know of are about 150 million years old. So birds are have a lineage that goes back to the Jurassic, and that's part of why we know that they're a form of dinosaur. They're just the ones that survived, really. So it's, instead of coming after, or I've seen it presented where it's a T-Rex is watching the asteroid coming and then just kind of becomes a bird. It's well, it's not really like that. It's they're actually well established, and that's the thing. A lot of these groups that even survived, there were mass extinctions of mammals and of birds and of lizards and snakes and all that sort of stuff. So everybody took a hit. It was just, was it total or not? But I like this idea that you're getting at, that all these sort of familiar sort of organisms or creatures that we think of as separate in time were actually interacting with each other.
Yeah, it took me a while to really kind of let it sit in my head that birds are dinosaurs. And I had to do a lot of, I heard that a long time ago, and I don't know, I just had to do a lot of reading, and I think when I read Richard Prum and a lot of his work, and I talked to him last year, and it just kind of really hit me And it was just like, yeah, because he found like the feathers, or was part of the team that discovered feathers on dinosaurs, and then like they were colored feathers. And his whole thing is that potentially that, feathers evolved for probably beauty or maybe even sexual selection or something like that, and not necessarily for flight, right? And that it did afterwards, but it had a multivariate function. And so now when I see birds outside, I was outside today and I saw just birds kind of hopping around, and I'll just watch birds, just little small birds that fly around, and then I just watch their movements, and I watch how they hop around and how they move their head, and like and then I'm just like, oh, they're dinosaurs, right? It's just like, it's, I don't know. I kind of only see it that way now, and it's weird. It's really kind of strange in some ways. It's cool, but it's strange to like grow up around birds my whole life when I was a kid and didn't even pay attention to them, or they fly in the air. And then it's like, oh, now as an adult, I'm like, these are dinosaurs and they're always around us, and it's like super, super wild. I don't know. It's a really cool thing.
Yeah, it is. I mean, that deals with a science called systematics. So that it's often related to taxonomy. So taxonomy is how we name organisms, and systematics is basically how we organize them. And many of us, like for me, I think the pivotal thing was like, what I learned it earlier, but I remember like in 6th grade biology class going through the classes of vertebrates, and they were all treated as very distinct from each other. But even then, it's like, well, wait, you keep saying that like reptiles have scales, but so do birds. They do on their feet. And there are certain, like, you say like, this is what fish do, but technically we are fish. So like nothing messes with your head once you start to understand, how we're trying to reconcile the natural world as it exists with a system to understand it, but in a way that like we can actually communicate with each other. So there are plenty of things where, all dinosaurs technically belong to a group of animals called dinosauriforms, which fits into a group called dinosauromorphs, which fits into another group. And it's like, so when you use the term dinosauriform, are you talking about a non-dinosaur form? So basically like a cousin of dinosaurs or not? And it gets very complicated very quickly. Like to just pick one other example, if we look at the taxonomy that now exists for, our favorite dinosaur T-Rex, Tyrannosaurus Rex belongs to a group called the Tyrannosaurines, which fits in a group called the Tyrannosaurids, which fits in a group of the Tyrannosauroids. And, all these things, like you need to kind of like know your Latin and your Greek, like roots and prefixes and stuff to like make some sense of like what comes before which thing. But like I said, we create these structures to try and understand. And when we kind of take a step back from that and just observe the sort of commonalities or differences that exist, all these different connections start to pop up. And I think it's fantastic that there's one group of dinosaurs that lived, and it actually has taught us so much, because once we recognize those, we're like, oh, there are all these traits that we used to think were super unique to birds that other animals don't have, like feathers or the system of air sacs that comes out of their lungs and invades the bones of their body and allows them to be very lightweight. All this sort of stuff. Non-avian dinosaurs had those too. They actually had them first, and that's where birds got them from. So now we can look at something like the skeleton of a raven and understand something new about a totally different animal like Stegosaurus or like Apatosaurus or whatever it is, that we have this kind of check now, or we can be like, okay, even if we can't observe all of these traits, we can at least infer that if crocs do this and if birds do this, and we know they shared a common ancestor and dinosaurs are in the middle, the non-avian dinosaurs probably did that or had that trait as well. And then we can start to test it. So it really was this powerful realization that unlocked so much. But I also love going to our natural history museum in town and watching the magpies jump around and be like, they look like little velociraptor, really. Like,
yeah, right. Yeah, it's super strange. And I don't know, ravens and have, absolutely fascinated me. I don't know. When I look into the eyes of a raven, I'm like, oh gosh, like that thing's peering through my soul. It's like, there's so much intelligence in there. It's wild. You just talk a little bit real quick before we get to the actual impact, is kind of a technical question, which is how we know all of these things about dinosaurs. So you talk about the fossils, and other people have looked at ancient DNA and things like that. How do we understand the details? And you talk about some of this, as you alluded to before, in the appendix about what we know, what we don't know, what we can infer and speculate. But what is the power of the fossil record here for dinosaurs specifically? And then we can talk about location and stuff. But yeah, what is the power of that?
Absolutely. So when we talk about fossils, it's not just the bones. Like the bones are super important, but there are things like tracks and trackways that are also fossils, or feather impressions and things like that. A fossil really is just like any trace of prehistoric life. So like a dinosaur just steps in the mud, leaves one footprint. That's just as much a fossil and can be informative, just as any bone from their skeleton can be. Unfortunately, we can't get DNA from them. DNA basically has a half-life, much like a radioactive material would. So I forget the exact time frame, but based upon calculations under even ideal circumstances, so let's say something like dies in a cave where it's very cold and it's very dry and it's amenable to preservation, DNA only lasts about 6 million years before it's just entirely gone. So that's still like 60 million years too short to even get to the very oldest ones. There's some talk of maybe like degraded DNA sort of biochemicals that we might be able to find, but it's kind of like trying to understand like what a burrito is from like the remnants of a burrito that was left out in the desert for 10 years. Like it can give you like some concept of the components, but not quite enough. Right. But in terms of what we know and how we know it, like a lot of this, it's fact and theory. It's something that goes back to like 19th century when science was really becoming codified. That you have what you have observed, and that needs to fit in some kind of system of thought or idea, and then you can start to check against it. So, for dinosaurs, for non-avian dinosaurs, the fossil record really is our prime example. We wouldn't know that they were here otherwise, and we're still finding them. A new dinosaur species is named on the average of every 2 weeks. Now, all of those become sort of permanent in our scientific understanding, but we're still finding a ton. We're still naming a ton of these things. And each time you find one of those questions is, okay, well, who is it related to? So you look at dinosaurs with similar bone structures and similar skeletons, and then you start to piece together where it fits in the family tree. And then you can say, okay, well, we have this better skeleton over here. So this new partial skeleton that I have, like maybe it shared some of the same traits or characteristics, so we can fill in some of those gaps. And that's a little bit of a guess that hopefully will be tested against better evidence in the future. But it's this constant interaction. It's not just finding a skeleton, sort of understanding this is what the animal looked like, because some skeletons we've had for well over 100 years, and the image of the dinosaur keeps changing based upon what we think now and additional evidence. One of my favorite examples is like right now, if you look at a modern depiction of Triceratops, you're probably going to see it with these big bristle-like structures coming off of its tail. Like, that didn't exist even 30 years ago. And in that case, it's not so much because of direct evidence. There's some fossilized skin that might bear on this. But because we found other horned dinosaurs with those bristle-like structures on their tails, and saying like, oh, if we're learning that most dinosaurs probably had some kind of like feathery or feather-like body covering, then Triceratops probably did too. And that'll be tested against future evidence. We can say, okay, yes, that's speculative, but it's sort of like informed speculation. I think I addressed one of my favorite examples of this. I mentioned at the end of the book in the appendix, there's a book called The World Before the Deluge that was published in the late 19th century. And it had this image, this woodcut of Archaeopteryx, the first bird. And at the time, we didn't know what the head of Archaeopteryx looked like. It was actually found on the same slab. They thought it was like a fish head, and they didn't realize what it was. But since nobody knew what the head looked like, the artist didn't want to draw it. So you have this headless bird soaring over this otherwise restored Jurassic forest. And that to me, it's like, that's when we get like a little bit too technically specific. Where you're almost like, well, we only have the bones. It's like, well, yeah, but we know that they're vertebrates and had a heart and lungs and a central nervous system, and they had skin and muscles and all these sorts of things. So if you try and be very literal with the fossil record, you don't get very far. But when you bring in that aspect of comparative anatomy, even if sometimes it's a hypothesis remains to be tested, that's what really allows us to start to bring these animals to life, is that we're constantly comparing what we're taking out of the rock to what we think we already know, and it's constantly checking against itself.
Yeah, that's super helpful. I like the way you explain it, because I think it's important to know the power of the fossil record, but then also kind of the ways in which it's creating a model to understand the record as well. And in the book you talk about Hell Creek. Where is this in modern day again? I'm forgetting.
Right. So Hell Creek is the main setting for the book. I shortened it. Usually we talk about the Hell Creek Formation, and that's a rock unit that we find in Montana and North and South Dakota. There are some equivalent rock units. For example, there's one called the Lance Formation that you find in Wyoming. It's the same time period. We just have a different name because there's slightly different depositional settings and all that kind of geological specificity. But Hell Creek, go ahead.
Sorry, where in Montana is it?
I'm not sure what the full extent is over the state, but a lot of the exposures are towards the eastern part. So if you go to towns like Ekalaka, Montana, or if you go towards Sioux Falls in Dakota, it's like that kind of area that we're primarily talking about. When you go out looking for like Hell Creek dinosaurs, it's usually towards the eastern part of Montana and the western part of the Dakotas.
I have family that lives in Montana, and I went the last time I went 2 years ago was to the Upper Missouri Breaks. And and so it's east, but not very far east. I've driven through there from North Dakota and South Dakota, so I've seen that part of the state just kind of driving through. And I remember driving through from western North Dakota into eastern Montana. It's very much like, yeah, isn't this the region where like the dinosaurs were and they find all the fossils? Like, oh, and then you're kind of there and you're like in big sky country and you see all of these like, kind of plains and you see these mountain structures and you're like, oh, let me just picture this. Obviously the world looked different back then and the environment was different, but some version of this was there and dinosaurs and so then I just start imagining like dinosaurs walking around. It's like, oh yeah, like how different was this back then or how similar? So I guess just tell us about the region. I mean, dinosaurs are found all over the planet, right? They've been found in China. They've been found in I think South America as well. Is that correct?
Yeah, the big thing when I was a kid was like, dinosaurs lived on every continent except Antarctica. But then we found them in Antarctica in like the 1980s and 1990s. So they really were all over the planet. And that deals also with things like continental drift. The fact that, we used to have like Pangea and that broke apart into like a northern half and the southern half and those split. And you see this reflected in dinosaur evolution, that as these land masses split, you get different communities or types of dinosaurs evolving. So in terms of the Hell Creek Formation in particular, it's this part of North America. There are some time equivalent rock units in Canada and other states in the US, but this is really the best known slice of time from the end of the Cretaceous. Because really what makes it so relevant was you have all this Cretaceous rock that's full of dinosaurs and all these amazing fossils, and then you have the break, basically the extinction line, what we call the KPG boundary. And then on top of that, you have the rock unit for the Paleocene, so the beginning of what we popularly call the age of mammals. So in other places in the world, you might have like the Cretaceous rocks, but then it stops at the boundary, or you have the Paleocene rocks, but you don't have the Cretaceous ones. So it's the fact that we have like the before and after snapshots in this particular place that really allows us to get some understanding of, okay, what happened here. There's a search going on around the rest of the world to say, are there equivalents of this elsewhere where we can get before and after? And there are some spots that look promising, but really like this is trying to understand a global extinction through this one relatively small window of North America. And that's why I set the book in this particular place, because this is what we know the most about.
No, it's just so cool that you can see the kind of before and after. Let's talk about the impact, the asteroid. So there are some really, I mean, again, it's just the kind of, it happened and then, they died and then we have mammals and that's all I knew. So a lot of this stuff I was, kind of realizing for the first time is super, super fascinating. Just tell us about, describe the asteroid as much as we know about it and how it's made of the carbonaceous chondrite. Is that right? Am I saying this right?
That's right. Yes.
And the speed at which they hit the Earth. Just kind of walk us through like what happened and what it was made of and how we know that.
Right. So this is kind of trying to reconstruct a crime scene almost. So like we don't have like a big chunk of the original asteroid. Like there are remnants of it. There are chemical parts of it that are spread all over the planet. But unfortunately, we don't have like a nice big piece of it in the center of this crater. So it's called the Chicxulub crater, that's found like basically under and around the Yucatan Peninsula today in Central America. So that was basically ground zero for this. That was the site of impact. And it's working kind of backwards from that to try and understand where this asteroid came from. We're not entirely sure. There are a couple of hypotheses about this. One of the current ones that came out within about the last year was that you have this big sort of debris cloud around the solar system called the Oort cloud. And it's kind of like remnants that didn't get pulled into the formation of planets or other sort of bodies in our solar system. And something knocked a big chunk of this basically out of its kind of stasis in this debris cloud. And by gravity, it starts to get pulled closer and closer to the sun, and closer to Jupiter. And these are vast differences, like measured in millions of miles. But like these fundamental physics forces like gravity still act on these things. And so best as we can understand, if this is the scenario by which this actually happened, this would have been like long before dinosaurs actually existed. So this wasn't like, something goes into motion the next day, it's there. This had been like coming for a very long time. It's like one of those, you never hear the one with your name on it. This is kind of like the cosmic version of that. So in this case, like as this body, this mass would have come near Jupiter and the sun, it would have kind of gotten stretched out and squeezed by the gravitational forces. And we've seen this happen with other basically comets and asteroids. There was one called Shoemaker-Levy 9 that was observed a number of decades ago, and that really was like a really useful example of like what happens when one of these asteroids gets close to a planet and might actually impact it. How does it behave? So it might be weird to think of something like an asteroid being like stretched out almost like a rubber band or like a hot dog in a sense, like in that kind of shape. But it kind of snapped in that sense. It got put under the stress, and then it basically got set on a new path, and it just happened to intersect with Earth's orbit. So Earth is moving through space, and Earth is also rotating. So you have all of these forces already in play, sort of the motion of the planet, both within its orbit, doing its rotation. This chunk of extraterrestrial rock that we've estimated was probably about 7 miles wide. So really quite large. Huge. But then again, it's huge, right? But at the same time, we know of larger impact craters on the planet that are not tied to mass extinctions. So that's what makes this one unusual. Like it certainly was very big, but it's not the biggest by far. And it seemed to be just like set up on the absolutely like worst path. Just like every opportunity that there was. If you think about all the sort of ways in which this asteroid could have gotten knocked off its path or become a bit smaller, or the Earth had been moving a little faster, a little bit slower, or whatever it is, all these things just lined up in pretty much the worst way to send it on this direct collision course into our planet in a way that's just like never happened before, with the exception of like the early bombardment of the planet that gave us a lot of our minerals and stuff now, but like hadn't happened in like hundreds and hundreds of millions of years.
And it hasn't happened since.
It hasn't happened since, right? We certainly have had impacts since then. I think just last night I was seeing something, which is my favorite new measurement, that there was an extraterrestrial chunk of rock that was about half the size of a giraffe that hit somewhere in the Atlantic. And I just love measuring things that way. It's like that whole like boulder the size of a large boulder kind of thing. So, right. But we're still being, we're still being hit, but just like not like this. This was very unusual, and this is very large. And the speeds here, I don't recall the precise numbers off the top of my head, but it's the asteroid is moving at a speed that's like greater than the Earth is rotating. So these are incredible speeds. So you have, you basically, if you think about something even as simple as a car crash, the faster those two bodies are going, the more devastating that's going to be. So this is incredible amounts of speed. And so far as geologists have been able to figure out, it probably hit at a 45-degree angle, I think, coming from a somewhat northerly direction. So it wasn't even like a perpendicular strike. It's kind of like varying in at an angle. And part of the story is the rock that it hits. So under any circumstances, a 7-mile wide chunk of rock hitting the planet would be bad news for the immediate area. You'd probably kill anything that's surrounding it. In this case, there certainly were mega tsunamis, so tsunamis that were like taller than skyscrapers that were radiating out and had so much energy to them that they hit the shore and then rebounded and basically infilled the crater that was turned into like molten rock and still churning around. Like within 5 minutes, the heat and energy of this basically turned the bedrock into liquid that which wasn't pulverized and sent to the air, and is sloshing around as these tidal waves go out, hit the continent come back again and infill it. So if you look at like geological sections that are taken from the crater, it's just chaos all the way through. It's just like, it looks like somebody put like a bunch of concrete in a blender, and that's the overlying rock. But the nature of that basement rock would be really important. So you have all this local devastation, but didn't necessarily guarantee a global mass extinction. And there are two parts to that. One of which I'm sure we'll get into in a minute is sort of the infrared pulse that happened, all this debris that goes up into the air, it comes back down, the friction causes heat and basically raises the air temperatures to like oven-like levels. But the rock that it hits is the remainders of these ancient reefs. So basically the remainders of these limestones that were created by coral reefs that used to exist in that place millions of years before. It's very high in sulfur content. And we know from a lot of our modern studies about global warming and global cooling that sulfates or sulfur-based compounds, when aerosolized and thrown up into the atmosphere, they reflect sunlight. So it basically has a cooling effect. So this is what contributed to that 1-2 punch that the extinction did, that you not only had the impact and the infrared pulse that occurred within 24 hours, but you had at least a 3-year-long period where a great deal of the Earth's sunlight, or the sunlight that the Earth would get, is being reflected back out. And it created an impact winter that lasted for years. Photosynthesis, like, all but kind of stopped over much of the planet. And that's all because of the particular place that the asteroid hit in that particular moment in time. So I like going into this in the book, like, if the Earth had been spinning in a slightly different way, or if it had been moving a little bit faster, if the asteroid had been moving a little bit slower, like anything that was just like slightly a little bit different, the extinction either would have been avoided or it would have played out in a very different way. Like, this was basically not inevitable. It was really the worst circumstance at almost every step along the chain, and that is incredibly unusual.
Yeah. Oh man, it's just so captivating here you talk about it. So I guess a few questions here. First is, I don't remember if you mentioned in the book, but how deep did it get to? Like, it didn't go to the Earth's core, but how deep did the asteroid hit? And then you talk about at some point where there are all these subsequent fires that impacted the Earth after the impact, and almost as if there were these kind of pockets of debris that were still kind of raining on the Earth, and then, like you were saying, kind of this oven effect. So there's that, and then the final third piece here is, so there's what gets decimated in the impact, but then there was the rest of the planet that didn't necessarily die immediately. Right, which we can get to, but so just kind of that instant impact, like how deep did it get to the Earth, what it destroyed in the areas around it, and then all of the other kinds of effects kind of rain down on it after the impact.
Right, I'm not sure about the figure on the actual depth, but it would have been within the Earth's crust, so it didn't penetrate down into the mantle or towards the Earth's core or anything like that. We're kind of riding on these plates that are made up of the Earth's crust that are always sort of shifting around. So it would have been on, certainly many hundreds of feet down. A lot of this is relatively hard to reconstruct because it distorted that crust because of the impact. So it's not sort of like it just leaves like a divot, or it's almost like a bullet hole where you can kind of see the shape and the direction it was going from. It's so fundamentally melted that rock, which then sloshed around like a liquid and folded over itself, that it almost covered up the extent to which it affected the planet. They immediately started to deform and then sort of reform in a very different way. But we're getting to the critical part of like what made the extinction as bad as it was. Like, when I talk about like this was the worst day for life, in the history of the planet, it truly was the worst 24 hours. So when I was younger and I'd hear about this extinction, I'd often see images of like T-Rex or Triceratops kind of shivering in this impact winter. It was based very much on like ideas of nuclear winter. If we had like an exchange with Russia, and it's kind of like this warning almost. And these dinosaurs were starving and they weren't make it. Fact is, they probably didn't make it that long. Most, if not all, non-avian dinosaurs on the planet were probably dead within 24 hours of the impact. And this is because of that infrared pulse that we were talking about. So when the asteroid struck, It not only melted the rock, but it basically pulverized a ton of rock and other sort of organic materials that was there. And we know it was a terrible impact because all around the planet in that boundary layer, you find little glass, basically beads, for lack of a better term. You find quartz, which is like, a mineral like amethyst, if you see that at your rock shop, or whatever, but it's like shocked. It's like cracked. It's obviously been stressed. So all these like little minerals, all these signs of like intense heat, intense pressure, all this stuff going on. So basically it hits and all this debris comes back up out and it goes up into the atmosphere. But as we know, what goes up must come down, and these things are heavier than the air is. So as these things go up and they start to spread around the planet, given air currents and things like that, they start to fall back down. And as they fall back down, each one creates friction. And any single one, that's nothing, it's minuscule, but this is just such a huge amount of rock. We're talking, basically like, hundreds of cubic miles of stone that have been turned into like these tiny particles spreading all over the planet. It creates so much friction that it creates an infrared pulse. So basically, if you think about like your oven set on broil around like 500 degrees or so Fahrenheit, the air was brought up to that temperature from all the heat, from all the basically this infrared pulse that the debris created. It was hot enough that if you had a relatively dry forest, that forest would spontaneously combust into fire. And even before it got to that point, there's nothing alive that can withstand that kind of temperature, maybe extremophile like bacteria somewhere, but like certainly any animal, any non-avian dinosaur. And we know that there were some non-avian dinosaurs that could burrow. There are some that were small enough that might have been able to sort of tuck underneath. But unless you could either get underground or get into the water, there wasn't anything that you could do. So basically, for especially the larger animals, certainly some of our favorites like T-Rex and Triceratops, there was no refuge for them. Like there's no way to respond to a crisis like this. So it was so intense that some geologists have speculated that almost all the organic matter that was exposed on the planet, so we're talking plants and animals and fungi, dead trees, living dinosaurs, were basically consumed by this heat, killed or burnt to a crisp. It was basically like the world was like on fire for pretty much a day. And then that died down. And it's after that, as the things that survived, like the small mammals and reptiles and birds and things like that, that were either in their burrows or things like turtles and frogs and lakes, that then they started to face the consequences of all those sulfur compounds that got thrown into the atmosphere, and you start to get that impact winter. So it was like a day of just incredible, awful heat that killed probably most of terrestrial life that was exposed on the planet, followed by this like very cold snap, this squeeze that went on for a couple of years. So it's like this terrible heat pulse followed by this really chilly impact winter. So whatever survived had to be, in a sense, pre-adapted, prepared in some way. Not that they could have done any preparation, but just had something about them that allowed them to cope with both this terrible heat and the cold that came after. And that's why the extinction was just so sharp. Like most other mass extinctions, when we look at them, they play out over the course of hundreds of thousands of years, maybe as much as 1 million years. It's still a very sharp uptick in the extinction rate. We usually calculate this by if more species are going extinct than are evolving, that basically they're not being replaced. That's what we count as a mass extinction. But in this case, it's a matter of days to years, which is incredibly rapid. And there's never been a mass extinction quite like this, where you can really pinpoint, basically down to a single day almost, that something like this happened. Usually it's much more protracted.
Yeah, I think it's interesting how you talk in the book about the parent rock and then the offspring rocks, which was super, super fascinating. And again, kind of what you're saying, this kind of what goes up has to come down. I guess what was, you were mentioning it, but the animals that survived. So it sounds like you're in the water, so you could, you could survive of sorts, although not all aquatic animals survived. And then if you could burrow, but some animals that could fly, I mean, they couldn't they couldn't be able to be in the sky. I mean, if it was 500 degrees, I mean, there's just no way they could survive. So I guess is anything more you want to say about the animals that survived, and then we can talk about the impact of light on Earth and how, again, I'd never thought about this, but the asteroid and everything afterwards blocked light, and so you can't get photosynthesis on plants and things like that. So yeah, maybe just talk about what were the animals that were able to survive a little bit more, and how, I guess, they were able to do it, not like during the impact, but then afterwards, right? The after effects.
Sure. So paleontologists have been wondering about this for quite some time. It's and we in general have wondered about this, like, why did the non-avian dinosaurs perish if they were so diverse and so widespread? Why did basically nothing make it through? And experts have been wondering, like, what's the filter here? What is filtering out the survivors from those that go extinct? And that's why the Hell Creek is so important, because you can get a more or less direct look at that and say, like, there's not enough time for the survivors to evolve into new species by the time we're getting the rock records from the Paleocene. So you can get a pretty good idea of, okay, like, who actually made it through this. So as you said, it wasn't total survival. Like, if you went in the water, it doesn't mean that every single species survived, or certainly those that went underground. I play with this idea a little bit that there might have been sort of raptor-like dinosaurs that were able to get into underground burrows. So they would have been small enough, they probably would have been able to take advantage of it. But there were effects after that that made life much more difficult. For example, there's a study that came out a number of years ago saying, okay, it's not just that birds survived, through the Paleocene to our modern era. It's that there were toothed birds in the late Cretaceous that didn't survive. There was a mass extinction of birds, as well as the non-avian dinosaurs. So does that tell us something? Because the birds that still had teeth, much like those little raptor-like dinosaurs, were carnivores. They were eating insects and small lizards and things like that, whereas birds with beaks had switched to a diet consisting of a lot of seeds, a lot of plant material. And that's what might have made the difference. So, like, even if you survived that initial pulse, in the stressed world that followed, where there's just not a whole lot of food, there's not a whole lot of resources, birds that had beaks that just happened to be able to digest things like seeds and nuts and stuff that were underground and safe from the fires, they were able to hang on, while those birds and raptor-like dinosaurs that had teeth and would have relied on insects or other animals to feed upon, they starved because there just was not enough food. And we don't know this, we don't have a time machine, we don't know 100% for a fact, but it's like the best working hypothesis that we have. So there are all these different kind of exclusion filters where it's like, okay, you're able to get past this particular stress, but there might be another one waiting behind it.
Yeah, you mentioned it's cool the way you talk about it in the book. You talk about, the first hour after impact, the first day, the first year. It's cool how you chose to write it that way. And so, after impact, and after this first day, what does it look like a month later, months later, a year later, and kind of tell us about how the blockage of light was not able to penetrate the Earth in the way that it does, and how that impacted, its ability to kind of, like, I guess, cool or to not cool down, but to kind of start rebuilding. Like, what was it's a huge, I don't want to say wound to the Earth, but it's this huge like impact. And then what was the Earth trying to do to try and, like, okay, we've had the impact. How do we kind of, like, repair? How do we kind of move forward from this huge impact?
Yeah, so after that initial pulse, after basically the first day, you have the heat dying down. There still would have been forest fires, consuming whatever sort of organic material was left in these forests that hadn't been burned already. So the Earth would have looked pretty well devastated. It would have been a relatively charred and desolate looking planet, where most of the life that survived was basically below the soil level in one way or another, whether it was in water, whether it was in burrows. They needed to be insulated in some extent. So you'd have these organisms that are starting to sort of peek back out, or things like, the natural seed banks that exist below the soil. In some ways, forest fires can replenish some nutrients and stuff in the soil. So they would have had something to work from. But at the same time, there would have been that cold snap that would have started to come in over months and over the 3 years after impact. It actually could have been way worse than it was. It's kind of, there's this whole other geological event that's going on about the same time. It started before the impact and it went on after the impact. Eruptions in this place in what's now India called the Deccan Traps. And it actually used to be a competing hypothesis for what caused the end Cretaceous extinction, but just it never seemed to work right. But an analysis that came out in the last couple of years figured out that the greenhouse gases that were spewed out of those volcanoes were able to cause enough basically global warming that the global cooling that the sulfur-based compounds created by reflecting sunlight is basically able to mitigate that just enough that that impact winter wasn't worse than it was. If that impact winter had basically hit the planet with its full force, then the extinction, I wouldn't say it would have been total, but probably would have been worse. It probably would be much harder for the surviving organisms to make it through. So in a sense, like this event that would have been devastating at almost any other time in Earth's history was actually part of the saving grace of these animals that survived. So that was those 3 years afterwards, where you have all these sulfur compounds that are reflecting sunlight. You have some of those greenhouse gases that are starting to counteract that. But photosynthesis still would have been basically curtailed, not halted 100%. You would still have plants like ferns that are, what we call a crisis species that tend to show up in disturbed environments, that tend to take advantage of sort of colonizing sort of disturbed habitats. So you would have started to see this low understory of fiddleheads and ferns and things like that starting to come up again in the wake of it, but nothing that truly thrived, nothing that truly like grew very tall, for quite some time. And it's this interplay where life is basically, it's starting to come back relatively quickly, but it's really hanging on. It's still under stress. We see this actually in the oceans. It's one of the best lines of evidence that we have about like how intense this was. And I go into this a little bit, like each chapter has a coda that like takes place in a different place around the planet. And there are these little things called coccoliths that are basically these disc-shaped algal organisms, and they kind of conglom together to make a sphere called a coccolithosphere. They're still in our oceans today. They're a really important part of plankton. So prior to the impact, you have ones that can photosynthesize, you have ones that can eat other organic material, you have ones that can do both. And after the extinction, you only find the ones that are really subsisting on other organic material. The photosynthetic ones have entirely gone extinct. So you have, for lack of a better term, this like kind of like predatory algae kind of thing that's crawling around in the ocean waters, just bobbing along at this microscopic scale. And they were able to hang on long enough, these surviving species, just by being fortunate enough to have the ability to eat organic material, that way when the impact winter lifted and they retained some of those old photosynthetic traits that hadn't really been in use, is able to kick back up again. They're able to diversify again. So it really like speaks to the fact that like without these organisms, without these things that were able to subsist upon other forms of life or organic debris, the oceans would have almost gone back to a single-celled state, which hadn't been seen in hundreds of millions of years. So it really was like this razor-thin margin because, we rely on plants. We require plants to survive. If you basically stop or severely cut back photosynthesis, there's nothing to base your ecosystems on. So it really was by again, just good evolutionary fortune that there were certain kinds of plants, particularly things like ferns or things in the oceans that were able to do this combination of photosynthesis and something else, that they're able to just like hang on just enough that it allowed the rest of life to make it through.
Yeah, I'm reminded of the thing that you're saying about ferns is super important. I'm reminded of the conversation I had with Patrick Roberts, who wrote the book Jungle, which came out last year. Great book. And he basically just tells the history of Earth through different tropical forests and how they're super important for many types of organisms and for different types of animals. And then he has a bit in there about dinosaurs, and there's this kind of how they interacted with the environment and how that was super important for them and then for the environment, and this kind of reciprocal relationship. It's super interesting how we think about animals and dinosaurs are super cool, and even for many mammals, but how big of an impact different types of plant life plays for many organisms on the planet. So
Yeah. And as you noted, it's this interaction between them. This is something that you see by the time you get to like a million years
Mm-hmm.
after impact, which is a very long time, but at the same time, like it's
Mm-hmm.
still pretty quick on geological timescales
Mm-hmm.
that you have basically these broad forests
Mm-hmm.
that are starting to spring up in the evolution of new plant life. And it's much closer and it's much denser than it ever was because during the time that the non-avian dinosaurs were dominant, there were so many large animals in almost like every continent, almost every landmass on the planet that just by dint of moving around and like where they move and the paths they take, like if you think of like game trails out in the woods, you can see where like deer regularly walk because they trample down the grass and things like that. Well, imagine an animal that's like larger than an African elephant
Mm-hmm.
doing that, and now herds of them, and like to the point where there are some studies that have hinted that where dinosaurs walk could have basically made like ponds or lakes, like they depressed the soil
Mm-hmm.
so much that it made a basin and then it created a pond, and there's a whole succession of things that happen after that. So in terms of forests, dinosaurs kept forests relatively open. They needed space to move, they knocked over trees, they certainly fed on a lot of these plants and trees. It's very much like sort of the African savanna today, even though like back then there weren't grasses yet. It's the same concept where there have been exclusion experiments done where if you take away the giraffes and the African elephants from today's grasslands, it starts to become more of a woodland. It starts to close up a little bit because these animals aren't making those paths and aren't knocking over those trees. So in the absence of those, basically anything big during that early Paleocene world, you had this very kind of mix of open habitats and forests that were big enough for like a dinosaur sized world become very dense and very closed. And that really became the crucible for the evolution of mammals and of the birds that survive and things like that. Because what like you were noting about jungles, particularly about like warm, lush forests, it's not just one habitat. There's the habitat that's under the soil and at the base of the tree and at different levels of the canopy and in between those trees. So it really is like a whole bunch of interconnected sort of smaller habitats that allow animals to have you can have like ones that fly or glide, ones that climb, ones that burrow into the bark or under the soil that live on the ground. Whereas like in a much more open habitat, you really just have like on the surface of the ground, under the soil, and that's about it. So what really assisted the diversification, the recovery of life was the absence of anything big, that life went back to being very small and is able to really fill up these new habitats that had never really existed, at least, not in that sense, for hundreds of millions of years. There were certainly forests long before that, but, during the whole of the Mesozoic, you probably weren't finding anything that's quite like, the jungles that we know today or that have shown up in the Cenozoic. So it really, again, was like one of these circumstances that provided the base foundation for life to start to take off in the way that it did during its recovery.
Yeah, it's super fascinating because when I was reading the book, that's what I was thinking about. It's like, okay, you have these 3 years of darkness, and obviously there's all the after effects, and then again there's another explosion of the biodiversity of life, right? And so it sounds like what you're saying is that there was quite literally fertile ground for that, and almost like a return to sorts, fundamentals, right? If you're doing things in kind of in a small containment, or you're doing things in a simpler way, then you just kind of build and there's able to just have this another kind of explosion of sorts, and which is interesting because there's a very big macro lens here, which is, for whatever reason, I don't think it's unique to the Earth, but it's all we know, at least at this point, is, life finds a way, right? Which is wild. And I'm talking about all kinds of life. There's been 5, maybe we're living in a 6th extinction at the moment. We've had the whole thing with the asteroid, and it just, life comes back again and again and again and again. And some animals don't make it. Sometimes they look different. Some do survive. Who was I talking with? I was talking with Dana Staff, who's she studies cephalopods, and we were talking about the nautilus, and that creature is just absolutely incredible. How it has remained pretty unchanged for millions and millions and millions of years in the ocean, because it's a very simple creature. But when you think about the history of some of these animals, and then but how they will restart again, it's super incredible. And so I guess on that note, as you move through the book, and you go from, the first year, and then you get to like 100 years, 1,000, million years after the impact, how do we just kind of build out from that? How does the rebirth of the new life start to interact in the different periods of the earth with land animals again? How do they begin to thrive? How does it happen with various creatures in the ocean? How do we get to, then millions of years later, a lot of this thriving from the initial impact?
Yeah, so there's a concept that's called contingency that, again, this is another one of my favorite tidbits from Stephen Jay Gould, where you have these certain events in life history, like a massive extinction, that you have the world is one way before it, and then you're left with a pool of survivors, and those survivors are going to determine the course that evolution kind of can take afterwards. So, for example, if after a mass extinction, you only have, let's say it wipes out everything on land and you only have creatures in the sea. This is just a hypothetical case. In that case, like, life is going to recover in the oceans, but it would require it's becoming adapted to life on land again, and it might not play out in the same way. It might be a different set of creatures. Whereas, in the past, we know that it was kind of things like scorpions and stuff were some of the first animals on land that came out there because there were already plants out there, and it was a particular kind of fish that's involved in our ancestry that then followed after the insects to munch on them. Whereas if we did this all over again, it might be different groups of organisms interacting in different ways doing this, and the history of life would unfold in a very different way. And like, the further you go back, if you make one of these changes, it's sort of like the butterfly effect, but it's like an actual sort of observable phenomenon. This has been observed in the lab, sort of with especially bacterial evolution, that if you feed them on a particular substrate, they'll evolve in this particular way, and that opens up some evolutionary options and closes others. So that's what's really going on in those earliest Paleocene days, is that you've lost all the non-avian dinosaurs. You've lost most species that were present on the planet. So this is really at the starting condition of those survivors, where if it had been a different mix of organisms, let's say for whatever reason, if mammals had been hit especially hard, but there was a greater variety of reptiles, and we might have had a second age of reptiles come about. Or the fact that even amongst mammals in North America, it was actually marsupial mammals that were the most abundant prior to the impact. And our ancestors and relatives, the placental mammals, were much more rare. If the marsupials hadn't taken a hit, then we probably today wouldn't view marsupials as these weird things that live in South America and Australia. They'd probably still be the most numerous mammals around, and evolution would unfold in a very different sort of sense. So that's where it's starting from, and it really was plants leading the way. It was plants that, after the fern spike that happened about 100,000 years after the impact, that's really when it hit its peak, that you start to get this establishment of these forests all over the planet. And there's a sort of, the after effects of, all those greenhouse gases and stuff that were still being pumped out into the atmosphere and causing forms of like runaway global warming, where it's like, okay, it's getting warm enough now that stores of carbon deep in the ocean or in, previously frosty areas are now being activated and creating this heat sort of spike, which is really kind of neat, because that 10 million year or so period after impact was very warm, was very lush. Researchers are studying that now to try and understand, like, what the global warming we're creating, what that is doing or might do, like looking at things like insect damage and things like that on fossil plants to sort of predict what's going to happen down the line. That's a whole other thing, but really it was the reestablishment of forests in a different way, and the organisms that live there. And if you look at a lot of the mammals or a lot of the animals that you see in these early Paleocene forests, many of them are generalized. You don't have any animals that are like a dedicated carnivore or an herbivore that's adapted to a very specific kind of plant. It really takes another 10 million years or so for those generalists to start to do what we call niche partitioning. It's the ability of animals to live in the same habitat by doing different things or feeding on different things. And that's when you start to get these specializations. I just wrote an article that came out today about the earliest saber-tooth that we know of. It wasn't a cat, it belonged to a different group of mammals. That's kind of, they were the top carnivores before cats and dogs really evolved. And it's about 42 million years old, so quite a bit after impact, but still like early in the age of mammals. And it seems to be a sign that by that point, you were getting beyond those generalists, that you were starting to have specialized carnivores, and then even more specialized carnivores that weren't even just like eating meat all the time, but like only eating the soft parts of the meat or having a very specific prey preference. So you have this starting state where everybody is kind of getting by on the basic stuff. But as adaptation and interaction and those evolutionary forces take hold, different species get shunted one way or another, and they start to do different things, and they start to live in different parts of the canopy or different parts of the forest and develop new ways of moving around or feeding. And that's when the diversity kind of builds on itself. And this is this idea that like, it's not as if nature is this void where it's constantly reinventing the same role or the same job for organisms, the same niche over and over again, as if there's like this invisible pull that there always has to be a wolf or always has to be a deer or whatever it is. It's the interactions between all these organisms that start to kind of nudge them one way or another. So diversity, in a sense, creates itself, that during these moments where you have these bursts of diversity, it's not necessarily because there are abiotic conditions that drive it. It's because there's something going on between the organisms themselves that are allowing some to specialize or do something different. And that's what you really start to see from those earliest Paleocene days through about the 10 or 15 million years after that, is that life is starting to rev that up all over again.
It's interesting the way you put it. I never thought of it that way, in terms of going from a generalist to more specialist, and then seeing how that really starts to kind of push it going forward. And then you can then you really just start to see the branches of the evolutionary tree start to continue. So I guess one of the final questions here is as we move forward in time, and we're 66 million years from the event of the dinosaurs and things like that, so we won't use the word domination, but we'll say that dinosaurs were pretty prominent. They were the pretty prominent land animals, if you will, for a long time. Mm-hmm. And obviously mammals have been pretty prominent more recently, including us. This is the Anthropocene. Is that still controversial? People still are fighting about that?
Yeah, it's something that like it makes sense. The people who coined that term, from what I understand, were primarily soil scientists. So it makes sense when you're looking at relatively short time scales. From the perspective of deep time, I don't want to get too dark with this, but it does make me curious, like what we call the Anthropocene. Is it going to look like another geological time period, or is it going to look like an extinction event? Because it hasn't been all that long yet. So that's one of those things, like time is definitely going to tell. We're probably going to be long gone by the time anybody names it, but it's an interesting thought. It's a good rhetorical device for sure.
Right. So the current period we're in, mammals, including ourselves, humans, are pretty prominent. What can we say, again, not to anthropomorphize too much or to always make this comparison with us, but I'm just trying to look at, there's these two periods, and we see a group that are pretty prominent. Dinosaurs in one period, mammals, and by another extent, humans. How do we see their prominence in these periods? What's different? What's similar? Obviously, the world's different. The environment is different. But just how do we understand what that looks like on a kind of a global scale on the Earth, and how it works?
I've always been fascinated by the fact that like our story really is deeply intertwined with this mass extinction, because when you think about our own ancestry, if you work back through those sort of classification schemes that we belong to a group called hominins that had many species, which are technically apes, which are technically monkeys, which are natural primates. The earliest primates that we know about are the same age and live in the same environment as Tyrannosaurus rex. That there were early primates present on that last Cretaceous day, they didn't really look like very much that we'd see around us today. The closest resemblance might be to tree shrews, which are once thought to be primate relatives, or probably something else. But these little shrew-like insectivores with these bushy tails, like if you kind of stretched a squirrel, that's more or less what you're getting at. And they were primates, and they were around for the extinction, and they survived. Actually, like primates, I'm not saying that we are directly descended from the primates that lived in Hell Creek, but they're at least an example that primates were around. They persisted through. You find this animal called Purgatorius, both in the latest Cretaceous and in the earliest Paleocene, in the same areas. So primates were already starting to make their mark on the world. They survived this mass extinction and then thrived through the past 66 million years with their own sort of radiations and extinctions and moving through the continents and that whole story. So we're really directly connected to this, where, you know, if things had been otherwise, you know, primates might have gone entirely extinct just as they started to appear. You know, just by good fortune they didn't, and that's part of what allows us to be here. And if that extinction had been modified or canceled, you know, we might not have ever evolved. That's part of that concept of contingency, that there's nothing inevitable about our history, that we're just the product of as many sort of like accidents and happenstances interacting with, you know, evolutionary forces, mutation, all that wonderful stuff as anything else. And I often hear people sort of compare us to, you know, the dinosaurs, which is a little bit of a lopsided comparison, because Dinosauria was this whole huge group of reptiles, whereas, you know, humans, like our species, only goes back 300,000 years. Hominins only go back about 6 million. If you want to broaden that to something equivalent, it's more or less mammals, which are just about as old as dinosaurs are. But let's say like that this happened again. Let's say like another 7-mile asteroid strikes the planet, the extinction unfolds more or less in the same way that it did. We probably wouldn't make it. Most life as we know it wouldn't make it. It would be a lot of creatures. I could really wonder about things like rats that would live, you know, in our subways, in our basements, anything that's underground. A lot of these animals that we treat as pests are relatively common. Would they become sort of the inheritors of the terrestrial realm? And it would be the sorting effect again, where it's like you would have these species that survive. They most likely would have to be globally distributed, have to live in some kind of sheltered environment that would buffer them against the extent of these things. But really, like, this just goes to show how much, like, how fortunate we are to be here. And I really love that there are so many signs of that Cretaceous world, or that world of recovery that came in the Paleocene, that we can still see. Like, one of the most recent discoveries that we have about that recovery is that beans, basically legumes, the first legumes that we know about, show up within 1 million years after impact that weren't present before. And these are very important plants because they are so rich in protein and so rich in many calories that it probably allowed mammals to get bigger and bigger. So again, this is sort of plants underwriting the story, and this is a change that happened only with the recovery. So, you know, whenever you have like refried beans, you know, in your taco, you're having something that showed up basically right in the wake of this terrible mass extinction. And it's something I've tried to think about, like, is there a lesson from all this that we can learn? Is there some way that we can, you know, take what we've gleaned from all of this and prevent it from happening again? I know NASA and other space agencies, you know, sort of watch the sky for near Earth objects. There's an experiment going on now where they're going to try and like use a satellite to push a meteor or asteroid basically out of its path to see if that's possible to do. It feels very Armageddon to me, which is kind of interesting. But I'm not sure that there is a sort of practical lesson to all this, as much as just wonder at the resilience of life that you said before. Like, life finds a way, and in some extent, that even if, you know, all animal life on the planet disappeared at the end of Cretaceous, microbial life would have certainly survived and continued to evolve. And who knows what the next iteration of, you know, animals or multicellular life would have looked like. So even though these events can be a little bit of a memento mori, that we know that all species eventually go extinct, that there is an end to everything, I like flipping that around and be like, how fortunate are we to even be here, that it's both sad and it's I'm not quite sure what the right word is. I'm not a spiritual or religious person. It's always like a blessing in a sense. It's this moment where it's like this inflection point where it really makes you think about like how you came to be here and what your history is and how different it could have been. And I know for me, it makes me certainly grateful that I exist, because any small thing that was different about the way that extinction played out, and like none of us would be here to talk about it. So it's one of those things that just kind of leaves you in awe of deep time and everything that came before and what we can understand about it. And it makes me wonder about the future. It makes me wonder what life is going to look like 66 million years from now. I wish I would get to see it, right. But I know it's going to be cool. That's all I can say about it.
Yeah, it's I think about that as well sometimes, where, when things in the world or things in my life or just in general, and I just think about it, and then I just like take a minute to like just zoom way out in time and in space. And it's like, we're on this spinning rock in one galaxy, and it's like, there's no recognition of any of this stuff. It's all sort of kind of relative, and some of it's not important. Some of it is. But sometimes it's that context, that big wide lens context of like, we're on one planet in one solar system, in one galaxy, in this one universe. When you go all the way, it's just like, wow, like we're so like it's such a crazy probability that we exist and that we're talking about this, and it just will blow your mind in some ways. And so it is interesting, when you're talking about a book with, we're talking about millions of years and all these things that happen, some of the perspective, which is kind of my last question here is what is it, the thing that you want people to get most out of your book? You put out all of your hard work in research into writing a book, which is really good. And what do you want to walk away with, where people pick it up and they read it and they say, that you can say, yes, that's it. You got it. That's what I was trying to say. You got what I was trying to say, and everyone's happy. What is that kind of thing that you want people to get from it?
Yeah, I'm not sure that there's a specific point that I want people to get, but I want people to go look. Basically, I want this to help make people curious the next time that, let's say they're at a museum and they're looking at a dinosaur skeleton, to really think for a second about, from whatever perspective that they want to get at it from, that you can think about, okay, am I looking at a cast or the actual fossil? And if I'm looking at the actual fossil, is this one individual or is this many individuals? And how long ago did it live? What was its day-to-day life like? Did it have mosquito bites? Was it sick? What did it like to eat? All these things that we kind of have these glorified images of the past, where dinosaurs often seem like very impervious, like right to the end, like, very regal and very like in the prime of health, when like they broke bones, they had diseases, they had cancer, they got lice, they had parasites in their mouths. They dealt with so many things that are familiar to us. And that's what I really want to help create, is this connection across time, and not think about them in an anthropomorphic way, but think about them in a way that we relate, that they were really alive. This is not just dead tissue that's turned to stone, that it's something that was vibrant and was vital and has all these stories intertwined through it. That's one of the reasons that I love dinosaurs. It's because it's not just the sort of fantasy of the animals themselves and imagining them. It's that they represent a lot of big ideas. Like, we get hit with this when we're young, and I think we should. I think it's a good thing, but it really kind of shakes your world when somebody tells you, okay, this is an animal that's real, and it was alive millions of years ago, and it's related to other animals that it evolved from, and it went extinct. And that was a long time ago. So like, just in that, you get the concepts that the earth is extremely old, that evolution is a reality, that extinction is a reality, that they're related to each other, that we're able to say something about an animal that like we'll never see alive, but we still have the records from it. We can tell these things about it. It's all these big picture, very powerful things. And I think, in a sense, even though this book has as much detail as I could muster, felt that I could, it's really that curiosity, that wonder, going like, well, what is that? And how did it move? And what did it look like? And what did it sound like? It's kind of like the shared sense of dreaming. And that's, I feel like we're missing that a lot in modern science literature. Like so often a lot of books, they're in the mode of sort of news you can use, or there's a particular angle that somebody wants to, like, they did a survey or a particular study. I'm not trying to denigrate anybody's work here, but sort of there's definitely pressure to, you find out one thing and then you want to make it an argument and say, like, this is why it's important to your life. Yeah. And I've never really been interested in that form of writing. I view this as a kind of invitation that, this is like, let's think about this together. And I hope by the time, the readers put this down, whether it's visiting a museum, whether it's something as simple as watching a honeybee pollinate a flower, which is something that's very, very ancient, or seeing a caterpillar chew on the edge of a leaf, thinking about, like, wait, I'm witnessing an interaction that's been going on for hundreds of millions of years and used to be part of a world that was very different from this. And it's still going on. It's still influencing my life and I do.
There's a connection there. There's a connection, right? Yes. Which is, powerful. This is very powerful that this thing, or just the caterpillar example or whatever, that's been going on for millions of years, way before like humans existed, before maybe even primates existed. Like that's been going on forever. And I'm seeing that, like we don't get to see all that sometimes. So it's a simple thing, but it connects you with time, and it can connect you to a time past of this planet when it looked probably nothing like it looks today. Like it's wild how that can work.
That everything you see around you has a past. Everything living has a fossil record. It might not be a complete fossil record, but we can go into the fossil record and say, there's a fossil example of this somewhere, and there's a connection to be made there. And that's really what I really love to do. There's something I like to do. I don't remember to do it every day as much as I would like to, but I often go on walks with my German Shepherd every morning. And as I do, if I see a wildflower, or if I see an interesting leaf or something like that, I like to just stop for a second, just like touch it, just literally like be in touch with that thing. And it's not necessarily even because, sort of the nourishing sense of nature or anything like that. It's just like, it's a connection. It's something interesting. It's something tactile. We live in such a world that we have constructed in terms of, our minds, our jobs, our society, and everything else. So I feel like sometimes it's easy to lose touch with those more vital senses, kind of like taking the pulse of something that's outside these constructs that we make. And that's really what I hope for this book. It's to leave people with this sense and this motivation to, like, take a second to, think about this question. Even if you don't have an answer for it, just thinking about it creates a connection. Touch something that, like, you would normally just walk by, stop and watch that jumping spider on the telephone pole for a minute, see what it does. Even though this is about the past, it's about dinosaurs, it really is about these threads and these connections that we can tease out from almost anything. And I think that's extremely powerful, because once you start seeing them, you see them everywhere.
That's right. Yeah, you see it everywhere. No, that's great. Two quick fun questions. Do you have a favorite dinosaur? And if you do, would you ever want to meet that dinosaur? If you could jump in a time machine, would you want to see that dinosaur and interact with it? What are your answers there?
Let me see. So this is always a hard one for me, because, like, dinosaurs are just so cool. It's hard to just pick just one. It's kind of like, what's your favorite pizza topping? I'm not sure how I can answer this without immediately having misgivings. But I think, at least right now, my favorite one is probably Allosaurus fragilis. So this is a particular species of Allosaurus that existed about 150 million years ago. You can find it, throughout much of the Intermountain West. It was like the most numerous carnivore of its time. Some of the biggest ones could get up to T-Rex sizes, but most were relatively small. But I love that it's an animal that's very familiar. We've known about it since the late 19th century. Its name, Allosaurus, just means different lizard, because so little was known about it at the time. It's something different. It's a different reptile. That's about it. But I love the sound of it. And I love that it's this familiar and abundant and fascinating animal that we still don't know a lot of the basics about. because it's not as popular as dinosaurs like T-Rex. So it's like we have the information, we have the bones, but I love that sense of mystery. It's like when you see these differences between its skeleton and other well-known dinosaurs, you're like, okay, but why is this different? What was it doing? How is it living? How was its environment different? All those questions that come tumbling out of it. And it also happens to be my girlfriend has an alter ego sort of character that's an Allosaurus. So I feel like I'd be remiss if I picked a different dinosaur.
That's funny.
And if I wanted to meet one, I probably would. I might, want to be careful about where I was walking in its environment. It used to live in these big floodplains, not all that different from the kind of, if you imagine like a big conifer forest, it's carpeted with ferns, and you have these stands of conifers that open out into these broad floodplains. And you have, in this environment, dinosaurs like Stegosaurus and Apatosaurus, and Allosaurus was the big carnivore. There's all this diversity. It really was like this time of dinosaur giants. So really not to see not only Allosaurus, but just to see this environment that is just so unlike anything around now that's such a scale that would probably make me feel like a very small mammal and recapture a little bit of that first museum visit where dinosaurs really first hooked me when I was 5 years old, and just just feeling so little next to those skeletons. I think that would absolutely be a wonderful trip to take.
And then the Jurassic Park question, if we could do it, should we do it? Would you do it if they said, okay, here you go, we can make some dinosaurs and we're able to do it, and okay, go ahead. Would you do it, or should we do it? What do you think?
Yeah, so I would probably be the Ian Malcolm of the group. I mean, granted, like Ellie Sattler also brought up like many of the same points, like many of the scientists come to the same conclusion, but say like, I'm not sure that we should. I've actually written quite a bit about de-extinction and whether it's actually possible, because that's one of the things that I find like an irony in Jurassic Park, right? Is that it's all about bringing dinosaurs back to life, but we know that they're not quite entirely dinosaurs because of the frog DNA, and they are behaving in ways and doing things that we can't possibly check or verify for reality. It's kind of like our best guess. So at some point you have to ask yourself, like, is this actually a dinosaur, or did I invent something brand new? So if somebody were able to be like, we not only have the genes, we also understand something of this dinosaur's behavior and what its nutritional needs and all that stuff is, and it's like, okay, maybe let's talk about that. I think that maybe we could do it. Right. But that's one of my favorite points, is like, we're so much more than sort of like the sum of our genes, that if that's what, like, Jurassic Park's geneticists came to me with, I'd be like, you got to show me something else here, or otherwise, like, people are going to get eaten by things that like never existed before. I will say, like, I've gotten to play with this a little bit. I'm actually the science advisor for the Jurassic World's marketing team. So since the first Jurassic World movie, I've done a lot of their fact-checking stuff on the toys and stuff that's appeared on the website and whatever. So it's been fun sometimes looking at the differences between the on-screen versions and what we know about the actual animals, especially in terms of like how heavy they were, and really driving this point home of like, sometimes we have this image of what these animals were, but then the more we learn about them, the more surprises that we get. Just to pick one really brief example, this dinosaur called Edmontosaurus that, was kind of, it's often called the cow of the Cretaceous, kind of everywhere at the end of the Cretaceous period, prey for T-Rex. Certainly we have, skeleton with bite marks on it. It's a very familiar animal. We've had complete skeletons since like the 19th century. You can find it at almost any major dinosaur exhibit. It was only about 10 years ago or so that we realized that at least some of them have this little like weird coxcomb, like beanie hat on top of their head that was preserved in soft tissues that we never had. So if we tried to recreate one of these animals prior to that discovery, we probably would have made it missing something that's biologically important to that animal.
That's a good point.
So that would be my argument for caution. Let's just say that, as much as I would love to romp with many of these animals,
right.
I would probably be taking Dr. Malcolm's side in this one.
Fair enough. That's great. Well, look, this was a lot of fun. The book is called "The Last Days of the Dinosaurs: An Asteroid Extinction and the Beginning of Our World." Where can people find the book, and where can people find you and your work and what you're doing?
Sure. So you can find the book basically anywhere that you can find books. You can get it from any bookseller. Definitely recommend going to your local bookseller if you got a favorite one and getting it from them. To follow my work, I have a website, which is just rileyblack.net. And then I'm on Twitter and Instagram at Laelaps, which is spelled Laelaps. And I share most of my work and other dinosaur and fossil related musings and adventures there.
Mm-hmm. No, that's wonderful. Look, I really had so much fun, not only talking about dinosaurs, but talking about dinosaurs with you. I love your passion, your work, your honesty, and it was just, the book is great, and it was just such a wonderful conversation. And I can't say enough thanks to you for having the conversation and just really being able to share so many wonderful things. It was quite enjoyable.
Oh, thank you so much. This has been a blast. Thank you for letting me just take off with dinosaur stuff. I can talk about this stuff for millions of years, it seems. But yeah, it's been an absolute pleasure. And yeah, next time you see a dinosaur, just ask it some questions.
All right. Thank you so much.
Thanks.